Engineer Janath, can you hear me?
Yes, I can hear you. Let's start.
Okay. Good evening, all. Good evening. I am Mohan from Building Service Engineering Sectional Committee. On behalf of Building Service Engineering Sectional Committee, I would like to warmly welcome you all for today's webinar. Today's webinar is medium voltage in installations in buildings. For that one, we have good resource person to describe the things. As a Building Service Engineering Sectional Committee, we conduct mostly the webinars, workshop, and so many educational events for you to upgrade your knowledge, day-to-day knowledge. So in Building Service Engineering Sectional Committee, this time we selected the very relevant topic for the building service engineers. The building, inside the building, we need to learn a lot of things when it comes to the medium voltage distribution. When it comes to the high-rise buildings, we do have a lot of medium voltage distributions systems in the building. So we need to learn a lot of things. So for that one, to give that kind of knowledge for you, we have organized this webinar. So I will invite Engineer Dilan Tilanga to introduce today's resource person, very expert resource person to the audience. Engineer Dilan Tilanga, it's over to you.
Thank you, Engineer Mohan. Good evening, ladies and gentlemen. On behalf of Building Services Engineering Sectional Committee of ISL, I warmly welcome you all to this insightful webinar of medium voltage installation in buildings. So today's topic is of great importance in the field of electrical and building services engineering. As we all know, the design of medium voltage systems in buildings is not just about technical calculations. It's about safety, reliability, maintainability, and compliance with industry standards. It requires a thorough understanding of protection schemes, cost implications, lifespan, and more, of all which are crucial for sustainable and efficient building infrastructure. We are honored to have with us this evening Engineer Kaushalya Alpitiarachchi, a distinguished chartered electrical engineer and the CEO of Amity Power Consultants Private Limited. With over 15 years of experience in the field of high, medium, and low voltage systems for diverse applications, Engineer Kaushalya brings invaluable insights into both design and practical implementation. He leads a multidisciplinary team offering services ranging from design reviews to electrical safety audits, compliance inspections, and more. His vast experience in commercial, industrial, and utility scale projects, along with his focus on practical standards compliance solutions, makes him the ideal resource person for today's session. We look forward to an engaging presentation followed by valuable Q&A sessions where we encourage all of you to interact and clarify the queries you have. There will be a moderator for this webinar who will be listing all over the webinar time period. You can shoot all the questions you have to the moderator through the chat box. So without further ado, let me now invite Engineer Kaushalya Alpitiarachchi to take us through this session. Engineer Kaushalya, over to you.
Right. Thank you very much, Dilan, and the team, the building sectional committee team, for inviting me for the event. Hope I am audible.
Yes, Engineer Kaushalya, you're audible and visible.
Thank you very much. Right. Thank you. First of all, I would like to mention Mr. Riansi Fernando, who was the teacher and the guru of me, and who involved me in all these applications of MV installations, and I take it as a chance to remember him during the presentation. So we'll quickly move on to the presentation. And this is, of course, a very vast subject. And I will have to run short on some topics, and we'll discuss some important matters which I found during inspections and visits. What are the areas that we have compromised, and what are the areas that we need to improve, and all. We'll focus more during this event. Let me share you the presentation. Sorry, it's pretty lengthy. We'll try to quickly go through this. Right, medium voltage systems in building. Voltage classification. It's from 1 kV to 52 kV. That's how the standards represents medium voltage systems. There are two distributions that they discuss: primary distributions and secondary distributions. Primary distributions are mostly the power delivery from transmission stations to utility distribution networks, and sometimes that may include other distributions, such as very large installations. Let's say earth resource installations, which is directly feeding from transmission station, or maybe a farm network which is distributed among so many acres and consuming more than hundreds of megawatts of power. In those cases, even the user may have primary distributions. The secondary distribution is a power delivery to the end user, most typically what we see around us. Some cases, part of the utility also may include in the secondary distribution. Yes, this purely we are discussing about medium voltage systems in the buildings. So we'll discuss what are the building types. There can be commercial buildings, apartment complexes, mixed developments. That means apartments plus commercial and some other amenities, hospitals, industrial sector buildings, data centers, substations, even electrical substations. Let's take the port city. You have a Indo electrical substation there. 222, 33, 32, 11. Then utility sector buildings, such as other utilities, let's say water supply and drainage board, such kind of utilities. Okay, medium voltage distribution system architectures. We can find radial circuits, which has a dedicated origin and a dedicated ending point, which are different from each other location wise. Right? Dedicated origin and a dedicated terminating point, which are different from each other in the perspective of location. This can be the cheapest method in most cases, and with less redundancy if a single feed arrangement is considered, and less complex as well, and ideal for applications that do not need redundancy power supplies or non-critical environments. Sometimes maybe for applications that utility provides a single feeder arrangement. But even though you have a single feeder from the utility, you still can have a ring circuit at your end, at the user's end. But if there are no much load centers for ME distribution, that may be not necessary, other than you need internal redundancy. Ring circuits. Ring circuits, of course, much complex compared to a radial distribution. In a radial distribution, your secondary, or let's say your utilities medium voltage primary panel is there, and you are getting a single feed from there to your secondary distribution system, and from that secondary distribution system you are having a dedicated connection, a dedicated cable which is ending at your load center. A ring circuit that forms a ring from the secondary substation again to the secondary substation, and your load centers are connected either through this ring or a tap off from the ring as a radial. Yes. So this engage with much higher complex protection schemes, and it is highly redundant because the particular center is being fed, can be fed by two directions, and it is costly and more suitable for environments you need lesser downtime and high redundancy or critical applications, or application which has higher number of load centers. Why is that? If you are going to feed radial circuits for many load centers, that means you are going to have an extensively bigger secondary distribution panel, which will occupy a very larger footprint. So you can lesser or reduce the footprint by having a radial circuit and distributing load centers among the ring circuit. Sorry, having a ring circuit. Yes, things to be considered when you are doing a medium voltage design network. Application type. What is the application? Whether that is going to be a data center, a hospital, or a housing complex, or a commercial building, or an industrial building. Safety of people, building, or the installation, let's say, and environment. Service conditions, mounting or installations, and transportation conditions. Reliability of the installation, maintainability of the installation, space, and the cost. Why space? Yes. If you take a per perch cost in a city limit, let's say in Colombo, somewhere around Colombo 3, Colombo 4, or Colombo 7, that's going to cost a lot. So space is a matter definitely for developers. So that is a big concern. And the cost. Cost will also a very big concern. Others also should be a big concern for a reliable and trouble-free installation. Right, let's take each section one by one. Safety of people, building, installation, and environment. MLE applications, of course, has much more higher voltage than the low voltage applications. So you need extra precautions and considerations during the design for fall protection, access restriction, even for electrical stuff. Some uh, competent and authorized persons will only be allowed to enter the HV switchgear room. Not even all the electrical staff are allowed. And the physical location. What do you mean by this? Where we are going to house these medium voltage equipment, and what are the impacts? We have to consider those. Clearances. Electrical clearances may be face to face, face to ground, and working clearances, equipment to equipment clearances, equipment to wall clearances, and passages and all. Earthing, which is a very important aspect which needs to be considered during the MB design activity. Applications. Nature of the business. So when we talk about the nature of the business, hospitals, data centers, these kind of businesses are critical or emergency installations which can provide lesser downtime and lesser maintenance activities can be permitted and need high redundancy, and protection and safety requirements could be very, very high. Monitoring and control. What to be monitored, what to be controlled, what to be monitored and controlled, who are going to monitor this, who are going to control this, who are authorized for that, what clearance do we need before controlling, and all has to be taken into account. Other than that, service and maintenance requirements. If we are not permitted to do regular maintenances, then we have to select equipment which has lesser maintenance requirement, or we have to have a schedule how to do this maintenance activities. Fall protection functions. If you take ANSI protection code list, there are about maybe more than 120 number of relay codes. So among them, in these building environments, we commonly practice very few relays like overcurrent, earth falls, and voltage relays. Those are the very common relay types in Sri Lankan context. And other required functions may be differential protection, breaker failure protection, earth fall protection, trip circuit supervision, and maybe some frequency related protections. And apart from that, depending on the application type, let's say it's an industrial application, you may need some other more protection functions, maybe liquid starters and related protection functions, maybe for motor rotor protection and so on. Access restriction. Yes, it should be very well practiced. I'll tell you one story. There was an incident very near to Colombo, and because of the negligence, one person lost her life. Actually, she's from a hired janitorial service, and because of not restricting access, she lost her life. And she was the only person making money to run the family. So medium voltage is that crucial, and even low voltage, but this is more crucial. Even the electrical staff to be restricted other than chosen few. Those chosen few should be well trained on how to operate the system, what are the safety factors, and what safety to be followed, what PP is to be followed, and all. The chosen people has to be equipped with. So you can either have demarcations like danger signs, or you can have lockable doors with key locks maybe, or password protected maybe, or with biometric protection. Whatever it is, the access should be restricted except a few people who are competent enough and authorized to do the job. Yes, we have two videos. Most of you might have seen these. We'll see one. That's clearance. That's what happened to you. If you are dealing with medium voltage or high voltage, and how severe that potential is. Okay, we'll next move on to the next video. Yes, how dangerous that is. If your protection system is not activated, the fault will be sustained until the utility trips. So it is mandatory and it is very important to select right protection measures, protection functions, and apply right settings and coordination among devices. It is very crucial, especially at medium voltage systems. Sorry about it. Location selections. Now you saw how dangerous that arc flash was, and so we need to locate these medium voltage equipment away from general public for more safety, or in a location that minimize the impact to the business or the work carried out at the building, as well as people inside the building, and lesser damage to the building and people during an arc flash or a blast. Because of the high potential, blast can happen, and that's going to be very serious. Practical locations for erection works and earthing and grounding. So we have seen some installations. The entire building is distributed on the land, leaving no space for your earthing, or sometimes evacuation, or to reach fire people, or maybe to load, unload spare parts, or to replace one of the medium switch gear. That finds a difficult situation.
Sensor തന്നെ
Pardon?
markane appe meme zoombarane prashne araka mamayanne meyoge
Yeah, I think everything's fine. Okay. And ingress control of dust, maybe liquid, or limit exposure to harsh atmosphere, or maybe smoke or contaminants generated by the application itself or neighboring applications. Liquids, in the sense, maybe uh, flooding. The flood levels has to be considered, and your location shall be selected with having an idea of the last flood level, and keeping an extra safety margin. You may have to decide what is the altitude you are going to place your switchgear and medium voltage equipment and loads, not only medium voltage, all the electrical equipment. Lesser disturbance to evacuation plan. Right. What is evacuation plan? In an emergency, we have emergency exit plan in a particular building. If you are locating your medium voltage system along this evacuation path, and the evacuation to be happen because of the failure of medium voltage switches or loads, then you are in danger. The medium voltage switch room is on fire, and your people needs to evacuate uh, just next to that particular building. So that has to be considered during your localization of switch rooms. Having easy access to installation teams to load, unload equipment and to be installed. Easy access to fire and rescue teams. Easy access to maintenance team for repair teams or utility to carry out their own jobs and move their equipment or test instruments. Clearances. Yes. When you are preparing your equipment layout, you should focus on clearances and to obtain enough space from your developer or the maybe the architect or structural designer, whoever it is, you need to prepare a sound equipment layout, allowing electrical clearances and adequate work clearances. Apart from all these technical things which are documented as standards, you may need to consider practical scenarios. Uh, how a person is going to handle this job and what extra space is required during a repair or moving a, let's say, a transformer out for a repair, or you are replacing a transformer. What is the most suitable path? What are the clearances you need? Those are, of course, physical clearances to take out the transformer. If you can't lift it or push it, you may need at least a forklift to lift it up and take it out. So you need to have adequate space for those. If not, you are damaging all other equipment which are situated or placed inside the particular switchgear room. And building up mutual heat. So that may increase the working ambient, and can cause damages. Yes, this is of course a compact outdoor canopy mounted substation having a transformer, LV switchgear, and a ring main unit. So see how confined that is. Of course, they have placed two equipment to open up to the front side, but the transformer is there in the rear side. The medium voltage ring main unit is towards your right side, and the LV cabinet is towards your left side. So see, that is pretty congested. So how a person is going to work there? Will it provide adequate space? How you are going to remove the transformer if you don't have extra door at the back? If you are designing such thing, you have to consider to have an extra door at the back, leaving space and make it possible to remove your transformer. Yes, this again another transformer obstructed with some spare parts, maybe switch gear. And to the right side of the transformer, you have some LV cabinets, and you see some handles there. That means those are removable, but that is locked with nuts and bolts. So the person who is removing should have adequate space to remove those nuts and bolts. And if any chance of replacing the particular transformer, we'll have to do some more changes. What about this? Yes. This has more than space available than required. Towards your right side, you have your ring main unit and one oil immersed transformer in a indoor environment. And the medium voltage cable also, they have done a covering with some foam insulation and have a cable box to cover the bushings. Clearances. Minimum electrical clearances. The standard is BS 162. Yes, the BS 162 provides you almost all the required clearances for indoor applications, outdoor applications, from building to transmission lines or distribution lines, whether they are bare or insulated, and so on. Vertical distances, horizontal distances, and all. So against voltage in kV, phase to earth in millimeter, phase to phase in millimeter is demonstrated. For low voltage, it is 15.8 millimeters for phase to earth and nearly 20 millimeters phase to phase. When voltage is increasing, you will see for 11 kV for indoor system, phase to ground 76.2, that means just below 8 centimeters, and phase to phase just below 130 millimeters, that is 13 centimeters. For a 33 kV system, phase to earth 222, just about 200, just about 22 centimeters, and phase to phase just about 35 centimeters in an indoor environment. Indoor ideal environment, I would say. You will find why I included that particular word there when you are reaching towards this presentation. Yes, is that actually enough? Distances, indoor substation minimum clearances, 0.9 meters horizontally between any item of equipment and the substation wall, 0.6 meters horizontally between any two items of equipment, 1.2 meters horizontally in front of any HV switchgear. Is it really enough? Different standards give different figures, but it is designers' responsibility to decide what is the level you need, because these standards have included the word minimum there. This is the minimum clearance, not the ideal clearance for the specific application or for the specific location. This is what is demonstrated by NEC standards or OSHAs, American. So there are three conditions that they discuss. Condition 1, medium voltage switchgear enclosed in a metal enclosure? If so, that falls under condition 1. Condition 2, medium voltage switchgear, open type, with exposed parts grounded. Condition 3, 2 medium voltage switchgears, open parts grounded. Depending on the voltage levels, the distance is increased. If you take a 33 kV system, in the first condition, they say that's 6 feet. Earlier case, it was like 0.9 meters. Here in case, this is little closer to 2 meters. If it is condition 2, that is 8 feet. That is more than 2 meters. In an application where similar to condition 3, it is 10 feet, almost 3 meters. So different standards have given different clearances. Anyway, in Sri Lanka, we follow BS, but make sure the designer decides what is happening there, what are the type of switchgear we have used, what clearance is necessary for the person to work. If it's a person like me, a fatter one, you need extra clearances for working. Yes, then service, mounting or installation and transporting conditions. What is clearance? We discussed clearance in earlier slides. Clearance is the shortest distance in air between two conductive parts. Yes. The diagram given, there are two conductive parts as shown there. The red color arrows demonstrate the clearance. The shortest distance in air between two conductive parts. And what is creepage? Creepage is the shortest distance along the surface of an insulating material between two conductive parts. These are two terminologies. Both discuss about a distance, but one is in air and other is on the surface. So mostly creepage distance will be higher than the clearance in most cases. Not in most cases, most probably all cases. Right. So why I am discussing about this clearance and creepage too much? Because this is one thing that we have noticed during our inspections and testing, which needs more attention to be paid. Pollution categories. This is being discussed and in several standards. IEC few standards 60664-1 insulation coordination, 60947-1, 60815, and IEEE C37.40. In insulation coordination standard 60664-1, it describes the pollution category in 4 particular degrees. Pollution degree 1, no pollution or only dry non-conductive pollution occurs. the pollution has no influence for the creepage. Pollution degree 2. Only non-conductive pollution occurs except occasionally temporary conductivity caused by condensation. What is that? Because of the moisture, temporarily that can be conductive, but not all cases. Mostly that is non-conductive pollution. Pollution degree 3. Conductive pollution occurs or dry non-conductive pollution occurs which becomes conductive due to condensation, which is to be expected. So in pollution degree 2, it's a temporary scenario, but in the pollution degree 3, that can be a permanent scenario, and that is the difference between those two. And pollution degree 4, the pollution generates persistent conductivity caused by conductive dust or by rain or snow. The most harsh or most severe condition. 60664 and 60947 both discuss the or given the same terminology for these pollution degrees. 947 is also similar to the particular 664 standard. Yes, 60815. This is what we refer for medium voltage installations. And this elaborates more compared to the earlier case. And the pollution level is also given by a different wording. Degree 1, light. Areas without industries and with low density of houses equipped with heating plants. Not designed for Sri Lankan context. Areas with low density of industries or houses but subjected to frequent winds and or rainfall. That means the deposits can be cleared because of winds or rainfalls, particularly for outdoor agricultural areas, mountainous areas, and so on. All the areas shall be situated at least 10 kilometers to 20 kilometers from the sea and shall not be exposed to wind directly from the sea. No direct exposure to incoming winds from sea. Medium 2, you have a description there. Heavy is the category 3, very heavy is the category 4. And this can be categorized into few applications like buildings situated near sea or isolated or away from sea, and so on. Yes, there it comes, creepage. If the pollution level is very light, you can have a creepage distance of 16 millimeter per kilovolt. If it is medium, the creepage distance shall be 20 millimeter for kV. If it is heavily polluted, 25 millimeters per kV, and very high, 31 millimeters per kV. So why this is important to the designer? Yes, the exposure of your medium voltage equipment to dust, dirt, or atmosphere, even though that's inside the building, If you go and see some installations inside of the medium voltage panel, or maybe the transformer, the dry type transformer, you have a hell of a lot of dust there. Sometimes if that is near the sea, that is conductive, a salty dust. So designer shall decide what is the creepage distance you're going to maintain and what is the uh, level of pollution that you're going to decide during the design stage. Service conditions. What are service conditions? Since this is medium voltage in buildings, we'll discuss this considering IEC 62271 standard. Yes, service conditions. It says does not exceed 40 degrees average or does not exceed 35 degrees over a period of 24 hours or does not drop below minus 5 degrees. No influence with solar radiation. Altitude limitation not exceeding 1000 meters. And if the ambient air is not significantly polluted, yes, you can refer 60815, what we referred earlier cases. And the humidity shall not greater than 95% over a period of 24 hours, and average pressure over a 24 hours shall be not exceeding 2.2 kilopascal. And there are some more service conditions and special service conditions. If you have special service conditions, then you have to refer, there are cross references to some other standards, specifically like insulation coordination 60071, high voltage insulation coordination. Because of the drop of pressure, if the altitude is increasing 1000 meters, the pressure is going to be dropped, and in that cases density of air can be, not can be, is different from the usual air density that may cause breakdown through air. Therefore, you have to refer insulation coordination and apply extra protection, insulation levels, insulation for your bus bars, or maybe you have to increase the distance, clearance, or creepage. For outdoor installations, generally it is considered at pollution degree 3 or above as required. For indoor installations, pollution degree 2 is generally considered, but the designer shall decide what level of pollution will be present. Either the designer should take precautions to lower the pollution degree from degree 3 to degree 2, or shall consider a higher pollution rating or higher pollution degree depending on the situation. But if you are to find indoor equipment, you may find it difficult to source some of the equipment if you are going for higher pollution degrees or pollution categories. So that to be kept in mind. That will leave us to strengthen or increase your infrastructure to limit the pollution degree to category 2, hopefully, for indoor environment. That is going to be a difficult task if the coordination among designers, other designers, maybe architects, maybe the structural team, or maybe the developer is not going to listen to you or coordinate with you. Hot arguments will be there. However, that's the real world scenario. Thing, a very crucial thing, and a very broad topic. So I'll try to limit it to save the time, and we'll discuss what are the most important things to be done, because any engineer who is doing earthing calculations, they know what are the standards and how to do that. But special concerns that's to be taken during earthing designs of a medium voltage system will be discussed. Relevant standards. What are the standards? IEEE 80, 2013. IEEE Guide for Safety in AC Substation Grounding. BS 761, 2018 with latest amendments. The IET wiring regulations. This is, of course, a low voltage standard, the ultimate standard for low voltage installation, but that have some topics like how we are going to interconnect those two earthing systems and so on, and what precautions to be taken if your medium voltage system is present there at your same premises. BS 7430 2011 with latest amendments. The Code of Practice for Protective Earthing of Electrical Installations, which describes how, what are the methods of earthing, and what architecture, how we are going to place them, how to bond systems, and so on. Within those three standards, we will find loads of cross references to many other standards to validate BIL, and to calculate fault durations and fault magnitude, insulation coordinations, and so on. There are two methods which you can practice, either one or two, if you are having your medium voltage system inside your building. Either you can interconnect the high voltage earthing system, or the, let's say, the medium voltage earthing system and the low voltage earthing system, or you can maintain a separate high voltage earthing system from the low voltage earthing system. So how practical this is? This may not be practical in every cases, but in some cases we may not have a choice other than interconnecting the medium voltage earthing system with the low voltage earthing system. If you have ample space where you can distinguish a clear separation, maybe more than 20 meters, from the high voltage earthing system towards the low voltage earthing system, the distance, of course, solely depends on your resistivity. Then, of course, you may be able to have a separate earthing systems for those two voltage levels. If you are interconnecting your high voltage earthing system and your low voltage earthing systems, this has to be considered and very well studied. You should evaluate the most suitable earthing arrangement at low voltage site. whether you're going for a TT or one of the TN systems or IT or whatever, specifics to the particular application. And reduction of overall earth electrode resistance. Yes, reducing your earth electrode resistance to facilitate grounding of the fault quickly. And maintaining touch and step voltage requirements. In IEEE it is, sorry, in BS 7671, you have a cross reference for few other standards regarding this. This is of course with the BS 7671. You can refer chapter 44 for the particular detailed jargon. Separation of high voltage earthing system from low voltage earthing systems have the same requirement. You have the same requirement, but not that crucial for reducing your overall earth electrode resistance. But some other factors may dominate the reduction of overall earth electrode resistance. So should evaluate the earthing arrangement and distance between high voltage earthing system and your low voltage earthing systems. Reliability. Any person who develops an installation, any user is seeking for the reliability of a particular distribution. So correct consideration of all the facts we discussed above will majorly help us to build a reliable medium voltage distribution system. Accurate calculation and right equipment selection will be a key factor. Protection coordination and insulation coordination. Yes, why protection coordination? If at a fault, because of a fault, your entire system is shutting down, then that's not coordinated. Because of a let's say during your operation, if your insulation coordination is poor, you will get frequent maybe arc flashes or faults, short circuits. So that will cause to reduce your reliability. Redundancy arrangements if necessary. Take a hospital or a data center or a critical application, you need redundancy. Maybe you need more than one MV feeder, or whether you have to check. The designer should decide whether you are going to maintain the redundancy through the medium voltage side or through the low voltage side. Whatever it is, redundancy will be a key factor for a critical installation. Sound testing and commissioning plan and sound installation plan. So whatever it is being selected to install, that has to be properly installed with good and acceptable workmanship, and shall be tested before energizing or before commercial use. So for that, you should have a sound installation as well as a testing commissioning plan. Comprehensive maintenance plan. For the reliability, after the installation, if you are decreasing your reliability, maybe because of your maintenance plan. So you need to have a comprehensive and sound maintenance plan prepared by an expert, referring so many standards, maybe equipment related standards or other standards like NFPA 70B, which discussed about all the equipment and all the scenarios. Availability of necessary documentation. Finding a single line diagram in some installation is difficult than finding Kalunika. So your documentation should be there. Most of them doesn't know where are the earth pits, whether this is a networked earthing system. None of them knows. No documentation is available. And trained technicians. In-house trained technicians will be a very useful factor for your reliability. Availability of spare parts. I don't say all the spare parts to be kept there, but at least a few which needs often replacements or which are difficult to source. Accurate calculation and right equipment selection. Under that, accurate demand calculation and fault level calculation. Yes, to save the time, I'm not going to discuss the demand calculations, as this is majorly fallen under LV calculations. Fault level, of course, yes, the energy divided by your impedance at the location. CT selection, switchgear selection, protection relay selection, detailed earthing calculations, which I'm not going to discuss because that needs much more time. Surge protective device selection, we'll glance it. Motor starter selection or capacitor band selection, those two that I'm not going to discuss today. Equipment selection, medium voltage panels. The standard 62271, the latest edition. You have two options: primary distribution systems, secondary distribution systems. Since we are discussing buildings, MVC distribution systems in buildings, we'll be sticks towards secondary distribution systems. There can be two options: air insulated switchgear or ring main units. Air insulated switchgear will occupy large flow area. The construction is simple, maybe lower initial cost, easy maintenance, but higher maintenance frequency and time consuming. Easy to install, expand, and test because you have ample space. Environmental friendly. Very less chemicals involved with other than lubricants and some insulation material. So that's environmental friendly and easy disposable. Ring main units, compact, very compact. Lesser maintenance if that's with gas insulation. Higher initial cost compared to AIS sometimes. Easy to install, but expanding may cause difficult in some cases, and repairing can be even more difficult in some cases. If you find a gas leak of a XF6 chamber, that's unrepairable. You will have to replace the whole switchgear arrangement. Because if it keeps on reducing the gas pressure, things are going to be very bad because air could increase after some level, and that will compromise the quenching and insulation inside the chamber, which will lead to a very catastrophic failure. Better fit for environments with higher pollution degree than AIS. Yes, because the RMU, it has a sealed switching chamber, or maybe sometimes the breaker chamber or bus bar chamber, because of the SF6 gas. So ingress of foreign objects is completely protected. Therefore, for harsh environments, this will be more suitable than an AIS. AISs also can be used, but will have much higher frequencies of maintenance rounds. Compromises in some protection functions due to the compactness. Yes, having wound type CTs will be an issue, and so on. So in those cases, some protection functions will not be able to be met. Disposal need much more effort because of this uh, greenhouse gases. Simple to operate and reliable. Circuit breakers, VCBs, compact, widely used, excellent insulation, excellent interruption, highly reliable. That is why it is widely used. Gas insulated SF6, excellent insulation and arc quenching and reliable, but banned in some countries where they follow Kyoto Protocol. Air circuit breakers very less common in nowadays in secondary distribution due to size and maintenance requirements, but still in use. In addition, earthing switch disconnectors and some other things there may be to facilitate maintenance. Internal arc classification. This is again another uh, area that we need to focus more. AF, AFL, AFLR. These are the three classifications. And standard withstands times maybe 1 seconds, 0.5 seconds, and 0.1 seconds. If you don't see any flap or any uh, chamber for arc classification, that means you are having a zero point 0.1 internal arc rated system. A stand for switchgear room with authorized access. F for protection for users from front of the switchgear. FL is for protection provided from front as well as sides for users. FLR, protection provided from front, sides, and rear, the full protection. This is, of course, a FL grade, AF grade, AFL grade, I think, yes, a switchgear. And this is AFLR graded switchgear. You see what are the differences, how strong they are, and you can see the cabin itself directs the arc towards the upper side, and the build is more strong. Circuit breakers, we discussed that. E2, electrical endurance. No surface is required for its interrupting parts. If you see a nameplate of a switchgear, this is of course a switchgear made by Schneider Electric. LF3, that is as far as I remember, this is a SF6 insulated switchgear falling under Schneider's product line. E2 is for electrical endurances. No service required of its interrupting parts. M2, mechanical endurance. Higher mechanical endurance like 10,000 tripping cycles at no load operations. C2, low probability of restriking during capacitive current breaking. Yes, that is called the avalanche breakdown. And when capacitive switching, if the utility goes and suddenly comes back, this scenario could happen. And just search for that. There are ample resources in the internet. This is another circuit breaker developed by ABB. HD4 is the model. It also has E2, M2, C2 classification and the standard 6227100 for circuit breakers. And one mistake the ABB has done, I presume this is not from Europe. UR voltage 12 kV Kelvin voltage. Even they have written voltage simple and K capital. Kelvin and some other notation for voltage. It is not voltage. Lightning impulse 75. These are the nameplate values. Operation frequency 50 or 60. Nominal current 1250 amperes. Short circuit withstand current 31.5. And duration 3 seconds. This is not the internal arc classification. This is the arc rating or the short circuit withstand current for particular circuit breaker. This does not apply for the whole switchgear system or the whole secondary distribution system. So don't be fooled by seeing 3 seconds. Your distribution system will not have the internal arc classification for 3 seconds. The breaker or the switchgear will have. And so on. There are so many things they have given. CT selection. Common types, wound type CTs, window type CTs, bar type CTs, and split core CTs, bushing type CTs, and CTs for cell power relays. This is a bushing type CTs where you use for transformers specifically. For metering and protection, both you need CTs. Accuracy class typically 0.2, 0.2s, 0.5, 0.5s, 1. If it is a 0.2 accuracy class, that means you have plus or minus 0.2 error at full load and 20% more from the full load. If it is a S class CT, you have very lower percentage error at lower currents compared to the normal CT. Protection classes can be classified 5P10, 10P10, 5P20, which means 5% of error within 10 times of its rated current value. Within 10 times of its rated current value. 5 denotes the error percentage, P for protection class, 10 for accuracy limit. You have 5P20, 5P10, 10P10, and so on. Burden of a CT. Burden is the total impedance of the secondary circuit, including all the components like cables, relays, meters, and so on. If the cable distance is higher, to limit the burden, you may have to use cables with higher cross sections. However, the higher burden will lead to inaccurate readings with increased errors. Lower burden, sorry, there's a spelling mistake. Apologize. A lower burden will saturate the CT and damage CT as well as connected equipment. Ratios may be 600 to 105, 150 to 105, 50 to 105. Yes, what are the ratios that we employ? This is a very crucial thing. And can someone tell me what is the ratio for the most suitable ratio for a CT for a feeder having a load of 1000 kVA at 33 kV. The current shall be nearly 18 amperes if you are using a 600 to 1 CT. How fair that is. If you are using 150 to 1 CT, how fair that is. If you are using a 50 to 1 CT, how fair that is. A 600 to 1 CT would not even recognize. Sometimes it will definitely recognize, but keeping the protection settings will have an issue. So you always have to select the right CT ratio. We'll refer this particular curve. The knee point is the 10% flux density, which causes 50% increase of the excitation current. If you plot excitation current over secondary voltage, you will get a graph like this, where the VK is the knee point voltage, where it's marked as knee point, and below that you have an ankle point. The most suitable region to keep your CT ratio is in between this knee point and ankle point, not letting it saturate during your inrushes, and make it possible to apply correct protection settings during your normal operation. And the ankle point, your metering CTs will always be below the anchoring point, and that will work fine there. If your CT's protection is CT is falling below the ankle point, then you still will have an issue, as that is not in the linear region. Your prediction will be very difficult. Apart from that, having a what do you call this, self-powered relays. So if your load is very low and the ratio is very high at self-power relay, during low load conditions, you may have issues of recognizing your load currents, because that needs at least 100 milliamperes to energize the relay. VT selection, similar to CT selection, burden, environmental condition, and accuracy class. It's not similar, but goes very closely. Auxiliary power and control power should focus on your reliability and redundancy. If you have your control power system for auxiliary supplies and breaker coil or control supply, then you need to provide the continuous supply for the protection system to activate. If your control supply is no longer there when it is needed to eliminate a fault, then there's no point of having such system. So you should have a redundant supply there, and that considerations to be considered very well during your designs. Monitoring and SCADA up to the level that you need. Surge protective devices. This has nothing to do with 62305. Your standard is 60099, or you can go with IEC 62.22. These are some specification jargon that you need to accomplish and finalize before ordering or before completing the design. And there are so many things: rated voltage, continuous operating, that is the UC, and that will be differed from design to design or distribution to distribution, depending on whether you have a directly earthed system at your substation, or whether you have an open connection, open delta connection, or a system that is unintentionally earthed. So depending on that, your UC value will be deferred. To select that UC value, you may have to use higher UR values. So that has to be looked at. The tables you have, that I see 600 and 99, and that's very straightforward. You have some classes, line discharge classes, whether it is heavy discharge or light discharge, and so on. So just visit the standard and you will see, and it is very straightforward. Design of medium voltage systems, transformers. Transformer types in buildings: oil immersed transformers, we see dry type, resin type, cast resin transformers. Which is more suitable? Can we come to a conclusion? Yes, before that, that needs following inputs: demand calculation, industry type, safety concerns, environment concerns, and location. If that's outdoor thing, you can have a oil immersed transformer. If the industry is having more harmonics, or that is referred to develop more heat at the transformer level, that means your dry type transformer is not going to work there. Or you have to employ extra cooling effects, or oversize the dry type transformer. If there is capacitive switching, definitely dry type won't be a good choice. Safety concerns: oil types will have higher efficiency, good in applications which increase transformer temperature during operation, good for outdoor and harsh environments, higher maintenance requirement, higher lifespan, lower initial cost, better performance, withstandability to surge, capacitive loads, and harmonics. Less safer in indoor use, less environmental friendly because of your oil disposals, ranging from lower capacities to very higher capacities. Dry type transformer, lower in efficiency compared to oil immersed transformers, lower in capacity also compared to oil immersed transformers. Max you see somewhere around 7.5 MVA to 10 MVA. Poor performance in high temperature. Applications where high temperature is produced at your transformer end. Higher initial cost, lower maintenance and lower maintenance cost, lower lifespan compared to oil immersed transformer, very high safety in indoor environments, poor withstandability to surges, capacitive loads, and harmonics. Environmental friendly during operation. If you are to withstand harmonics, you will have to oversize the transformer and have to equip with uh, extra cooling fans. So oversizing depends on your K rating, or you can have a K rated transformer. That's a bloody meaty transformer, which can withstand and live with uh, harmonics. That doesn't provide the efficiency. That's not efficient at all. What we have to do is we have to filter those harmonics using maybe active filters or passive filters or any other mechanism, and make the system efficient. Dry type transformers are the best for applications like apartment complexes, commercial buildings, data centers, hospitals, where you have very less or no capacitive switching or high inrushes. However, harmonic filtration is a must. Can we have oil immersed transformers inside buildings? Yes, we can have in some installation under very specific and safety requirements, having with oil catch pits, oil drain lines, and oil collecting pits, and very comprehensive automated foam-based fire protection systems, and at locations with minimal impact in a blast. Now we'll see what sort of a blast we are going to take. That's the oil immersed transformer, and that's how the blast happened. This is, of course, inside the substation, uh, outdoor substation, and a larger transformer. Even though it is a small transformer, keeping an oil immersed transformer under your uh, in your basement is like keeping a bomb inside your building. So if you really don't need a oil immersed transformer, better to avoid it. Even you have these catch pits and drain pits, if those areas the oil there catches fire, it is pretty difficult to suppress. The particular installation, the particular blast took more than 12 hours to stop the fire. Yes, protection requirements. Pollution degree. For indoor, we discussed that it is the degree 2 to be maintained. Overcurrent and earth falls, transformer differential protections. You know that in all the designs we see overcurrent and earth fall protection, but we rarely see transformer differential protection in the context in Sri Lanka. That's a very vital protection scheme and protection function, which can improve the lifespan of your transformer. And differential protection can is very sensitive and can address faults quickly, ranging from earth faults to short circuits, winding failure in the transformers, and so on. And that can reduce your downtime by early detecting your faults. If you have a harmonic environment in your low voltage side, so better to implement transformer differential protection. Apart from that, you should have uh, restricted earth fault. That is, of course, from your low voltage winding towards your LV panel board. So I'm not discussing those stuff during this presentation. Cable selection, usual steps. In addition to that, cable type matters, short circuit rating of cable matters, end termination type matters. Cable type, you may have mostly armored cables with steel wire armored or tape wire armored. If your installation needs burial and subjected to high mechanical forces, steel wire armored cable would be the best choice. The tape wire armor, if it is inside the building and for light mechanical damages, tape wire will be suitable, and it is more flexible than the steel wire armor cable. Because of the lower current level, lower steady state current, any cable usually goes okay with your installation cable design. Cables manufacturing start from maybe 70 millimeter squared, and which can accommodate somewhere like 200 odd amperage. at 33 kV, a 2 MVA transformer is using somewhere around 35 amperes, and a 70 millimeter cable having a 70 millimeter cross section is more than enough. But what about the short circuit rating? That has to be calculated and see. In a 70 millimeter squared cable, you may have somewhere around 6 Ka of a short circuit rating for 1 second. If your system needs much more requirement in short circuit capacity, if even though you selected those internal arcs systems and switch gear rated for 20k 1 seconds or 20k 3 seconds or 25k 3 seconds, you have compromised your design at your cable end. So calculating the short circuit rating is a must for the cable selection. Protection coordination. If you have protection coordination, it will sequentially trip during a fault. If not, sometimes the main circuit breaker would trip during a fault. Documentation to finish the design. You should have your drawings, maybe single line diagrams, layout diagrams, and other specific drawings to give a clear understanding to the supplier, manufacturer, or the bidder, and a technical specification which provides what are the standards, what are the technical values, and what are the pollution levels, and so on. For the manufacturer or supplier to supply the correct equipment. ME system installation is again a very crucial event. If that's not been met, definitely your effort during the design stage will be wasted. So time is reaching to the end, and I will have to rush through this. HV components shall preferably in a separate room from LV components. Flow preparation, leveling, trench layouts, oil catch pits layouts, drain layouts, flow material, ventilation design to be carried out in a very good manner. I'll show you a few slides, few photos, of course. What happens is the flow level is not in order, and adequately sized fire doors at adequate locations. If possible, anti-static flow, fire detection and protection, adequate front and rear space for maintenance, testing, proper cable termination, right gland plates materials and gland plate sealing, carpets or high resistive material to maintain touch and step potential inside the indoor substation. During the ME panel installation, if the level is not being met, reliability of your ME panel will drastically decrease because of crack formation of insulation or bus bar and malfunctions in draw out breakers. Sometimes you may not be able to rack it in after you rack it out. In this particular image, you see because of not leveling the flow well, the user had to use a small washer to lift the circuit breaker to engage the interlock when you are racking in. That is totally because of not leveling the flow. Sometimes you will find issues in related to interlocks and earthing switches as well, especially if that's an AIS system, because longer rods will have to be used as the panel construction is bigger. In those cases, some torsions and unwanted stress will apply on those areas. Transformer installation, same thing. Floor should be level and so on. We need carpets, earthing paths, earthing cables, and earthing bars to be there at right places, at right distances. Yes, this is the first image. This image shows you a SF6 insulated, maybe 30 kV distribution. And the flow is an anti-static epoxy-based flow and a gloss flow. And here, indoor installation with oil immersed transformers with catch pits, and there should be drain pits, which we don't see here. And again, anti-static flow with mat formation, another anti-static flow with mat formation. So if you maintain the environment like this, then you definitely will have the right pollution degree inside, and your lifespan and your troubles will be very less, and the reliability will be high. Cable installation, the most critical part. If you see, there's a small black dot here in this circled area. Do you believe that's the culprit, the ultimate culprit for the blast of this particular cable or flash over of this particular cable? That's the residue happened during your cleaning process of the semiconductor layer, which will formulate partial discharge in the longer run. And this is another example. And higher bending radiuses than required. This is the right formation during the installation of your medium voltage in termination kits. And different type of termination kits. This is a type C, and this is a plug-in type termination. Sorry. And this has a piggybacking kit or extender, which you can house your surge arrestor, medium voltage surge arresters in a compact ring main unit. MV panel testing. You refer 62271-1. You have a series for mandatory type tests and other type tests, and optional type tests depending on the manufacturer and the purchaser. You can refer 62271 part 6. The complete detail is there. And test after installation. Voltage test for main circuits. This is again called the high voltage test or high pot test, and it is said to be tested at 80% of the power frequency test voltage, and so on. You can refer chapter 7 of 62271-200, and a list of other standards, other tests. Visual inspection by an expert, high potential test, insulation test with DAR and PI. DAR is the ratio between insulation resistance, 30 and 60 seconds. PI is 1 minute and 10 minutes. A soak test for 12 hours. Earth electrode and earth continuity test, functional test for operational interlocks and indications, transformer ratio, vector group, winding resistance, and oil related test, maybe oil BDV, DGA, moisture level, dielectric, other tests, and so on. Yes, do we need to check ratio again and again as a routine test? No, we don't need, because those ratios are not going to change, even the vector group. Partial discharge test, phase sequence test, protection relay test, contact resistance test, breaker trip time analysis test, as a commissioning test. If you need, you can do it during routine inspections also, but not a must. This is for routine installation, same thing, but except few that you don't need to do. And high potential test on cables is not recommended frequently, especially DC high pot tests. You can do it as a commissioning test, but not as a routine test. If the system is getting older and older, you may have to do some other tests to check your insulation level, like tan delta and winding capacitance test and the leakage current test. Will be, if you are doing the tan delta test, you will get all these those two also during the test. Co-magnetizing current for your transformers, and Furanic analysis, especially for your oil immersed transformers. If you are exceeding maybe a lifespan of 15 years, it is recommended and shall check. Maintenance, cleaning for dust, contaminations, lubrications of mechanical parts, replacing of worn parts, maintaining IP ratings and necessary improvements. Check and clean your ventilation system. Check surge arresters timely and replace. Visual text checks for deterioration, damages, or yes, damages, loose connections and contaminations at connection ends, and electrical tests such as partial discharge, thermal imaging, leakage current, or maybe insulation. Any other refurbishment work found during routine testing work. So do remember to use approved chemicals for your cleaning and cleaning contaminations, cleaning dust and cleaning dust contaminations. And we'll see some images that I have captured, not of course me, team engineers of APCL, and see how severe those are. These images show some contamination of this copper tubing, dust contamination. Just see the level of dust there on your insulators and on your bus bars. That will bring down your bring up your pollution degree from level 2 to level 3. If your humidity is not controlled, then you are definitely going to have issues there at your installation, which will lead to voltage tracking and later on will develop partial discharges. Here you have you can see a flash over a previous incident. A damaged LV winding of a transformer. This is of course a dry type transformer, a cast resin transformer. This was employed in a high surge generating and high harmonic area. This transformer was replaced for 3 times. See what's the cost. Voltage tracking. Incorrect or unorthodox installations, leading the system to generate voltage tracking. You clearly see the barrier phase separator is touching your end termination kit and decreasing the clearance as well as creepage, which ultimately developed till partial discharges. You can see voltage tracking also at the shed, the upper shed at the bottom area. This again a scenario that has voltage tracking. You will see some dust deposits and maybe the insulation cleaning and stress tube installation of the particular medium voltage termination kit might have not done in a proper way. So the partial discharge is developing and will prematurely fail the cable system. This is another example of partial discharges and voltage tracking. So less solutions if you found it there. There's a new installation and maybe a couple of years, less than 5 years, because of poor installation work, it has developed. And yes, you can apply some paints, silicon based paints, but for a limited time. You'll have to redo the cabling work for a proper installation, and that will incur another cost. If you fail to see this, if you do your frequent maintenance, you never will know you have partial discharge until you hear your hissing sounds there at your MV switchgear panels. Ultimately, a blast there at your MV switchgear panel. Now we see what will look like a flashover. This is a flashover due to existence of this partial discharges, and this reflects very poor insulation uh, workmanship. In these areas, it may have had with air bubbles during the heat shrinking. See the energy dissipated and the damage happened to the medium voltage distribution panel. This is the place where the fault originated. Hopefully, most probably that tiny black spot can be the reason. The leftover of the semiconductor on the insulation might have, or a water bubble which is being left by improper workmanship. Yes, listen carefully. Yes, due to inadequate maintenance, poor installation, poor workmanship, and poor testing plan, the installation has caused partial discharges and voltage tracking. In a low light condition, you clearly see that, and you will hear those sounds. If further propagated, this will go for a flashover. Right, the time has almost hit the wind up, and I would like to stop the lesson here. And thank you very much for participating, and thank you very much for the Building Service Committee for giving me the opportunity to have this discussion with you all. And I would like to thank my office staff as well for providing with all these images and supporting me during the presentation and during the preparation of these slides. Thank you very much.
Thank you very much, Engineer Kaushalya. And there are some questions for that. And actually, this is one of the highest participant uh, come to the this webinar. And actually, it is almost above 145 participants were there at that time. And the questions are, Actually, there are several questions. Uh, Engineer Bandar asked that, can you please clarify and give more information about short circuit protection?
Yes, short circuit protection. Uh, you can have under few different NC codes uh, for short circuit protections in medium voltage switchgear. You can use 50 as the overcurrent with reduced time delays. The 50 code is for short circuit protection, and usually you shall limit your time delay according to your requirement. If when you're doing the coordination work, if your lower level to be kept at a lower voltage, lower time span, and shall be coordinated uh, towards the upper hierarchy. And the protection coordination and the short circuit study shall be carried out for proper and better set points.
Yes. Then Engineer Rukshan asked that, please give design standards. He
Design
asked that.
standards.
Yes.
Design standards in the sense I have mentioned few of the standards. You have to get all this information from those standards. For metal clad installations, 62271 range will have to be used, which includes all the necessary standards for the medium voltage circuitry design. And after that you may have to use standards for CTs like 60044. I think that's obsolete, 60128 or something. I can send it to the BSEC, and they can share it among the participants. And apart from that,
Sure.
standards for earthing, which I have mentioned there, and insulation coordination 60071, 60664, and coordination and the degree of pollution 60815. I think they also listed there. For transformers, you can use IEC 60076 from 1 to 11. Uh, Probably those. I shall send an email including all.
Thank you, Engineer Kaushik. And Engineer Mohan is asking that, we are construction a 8-story hospital building and MV room is located in second floor. How safe is this?
I think you have the answer there with all the aids that I have given during the presentation and the videos I have posted. That depends on your structural rigidity and how away from your general public and what equipment is used inside the switchgear room. If there's a dry type transformer, of course, probably the blast won't be that much drastically catastrophic. But if it is a oil type transformer, definitely you will have issues. And if you maintain all the correct values that we discussed, then you will have lesser problems, and better to have a very sound maintenance and testing plan and selection as well. And I would say if I am the designer, I would rethink having it there, or I would increase protection measures and safety measures.
Thank you, Engineer Kaushal. And Engineer Saranga asked that, three questions. That first one is, what is the best suited circuit breaker type for Sri Lankan application? Um, and then ask that him what is the best combination of CB type and switchgear type.
The second question, what is the best?
Best combination of CB type and switchgear type.
Uh-huh. Uh, Circuit breaker type. That
That he's giving the example SF6 switchgear with SF6 breaker.
right. Okay. The best switch, the best breaker type. That depends
Yes.
on your application. If your application somewhere near the seaside, then the air circuit breaker or a ACB is not a good choice. And FF6 breaker would be a better choice compared to even for the VCB. Even though the VCB is widely available, the SF6 is fully enclosed in a metal container, and VCB is also okay. The interrupter is there in enclosed, but you may need some more service intervals if you are using a VCB. So that depends on your application. If you are in a remote place away from harsh environments and a good sealed environment, your switchgear panel is in a very good sealed environment, there's no issue if you are going with ACB. VCB will be the most preferable option because of the availability as well as the higher insulation level and quenching ability. The combination of switchgear and breaker, that is of course again depends on your application. If you have enough money, you can go for SF6 insulated bus bar chamber with SF6 insulated breakers. That may be more than twice as a AIS, air insulated switchgear. Maybe more than 3 times even. If cost matters, then you definitely will have to step down. A, SF6 breaker or a SF6 busbar chamber with a VCB or SF6 breaker with a insulated bus bar in medium of air will be a better choice, which has a balance in the cost as well as protection. So I would rather like to go for a SF6 breaker or a VCB with a air insulated bus bar system with protection with the extra insulation layer, or bus bar in a SF6 medium with a VCB.
Yes. He has another question that do transformers used in solar PV application require special winding arrangements due to the high daily variation in power transfer?
Yes, of course, yes. Because of intermittent surges generated by your inverters, as well as uh, if you have higher harmonic contents, you need to consider those. That's why your K factor transformers are there, or you can oversize your transformer and have special cooling for your transformers. Preferably, you may use oil type transformers in an outdoor environment. If you have other compromises, you may use indoor type transformers with oversizing according to the K rating and excess fan, better not to size the transformer considering the capacity increment because of the fan. You will get about 20 to 30% of capacity increments because of the ventilation fan, but better not to consider that increment when you are selecting the transformer, a dry type, hopefully during a if it is an application where you are having it in it for a solar system.
Then engineer Lishani asked that please explain the quality test usually performed for high current breakers like 3200 amperes.
That is, of course, not the MV case. Okay, if a breaker is taken, you have different protection arrangements, different protection functions, a long time trip setting, a short time trip setting, or instantaneous trip setting. The short side trip setting, you have to calculate your let through energy, and long time trip setting, that goes under a curve. The If you check the curve, you have those LSI regions clearly demarked. So you have to check whether your breaker is going along this curve by injecting couple of times of your set current of your breaker. All the time you may be not able to, if it is a 3200 ampere, if you are going to inject 4 times of that, then definitely that's going to be somewhere around 13,000 amps. So giving 13,000 amp is much difficult. If you check with the curve, it may take few seconds if it is an electronic trip unit to trip. So that is very dangerous and very difficult to do in a non-laboratory environment. So in that case, we can derate your protection device to a possible current and do check it, uh, and check whether the from the injected current, what is the deviation for the calculated trip setting time. If the deviation is accepted within the limits given by the manufacturer, that product is okay to operate.
Yes, then finally, engineer Danushka asked that can you please show an example design calculation in medium voltage?
Uh, a calculation. Yes, I can, but that will take some time. I shall send it to the BSEC team, so they will be able to circulate among you guys. Hope that would be okay.
Thank you very much for Engineer Kaushalya for giving such a great presentation and good knowledge sharing session. And now, Engineer Janath, it is for you.
Thank you, Engineer Kalna. I hope you all have a valuable lecture on medium voltage installation in buildings, which is directly related to the building service engineers. So now it's time to show our appreciation to those who helped to make this event success. First of all, I would like to thank today our resource person, Engineer Kaushalya Alpitiarachchi, for accept our invitation and delivering insightful lecture today. We truly appreciate your valuable contribution for present this lecture by dedicating your valuable time and effort. Further, I would like to Thanks, Building Service Engineering Sectional Committee and the ISL staff for their support in organizing this webinar today. Finally, thank you all the participants for joining with us today by dedicating your valuable time. So finally, thank you all the people. We look forward to your continued participation in future events as well. Thank you all. Good night.
Thank you. Thank you. Good night. Thank you, Engineer Kaushalya, for a valuable session.
Thank you very much for inviting me. Thank you again. Thank you, everyone, and wish you all a good night.
Thank you.
Thank you.